We are discussing data-driven techniques in science and engineering. And so far we have talked about regression and then optimization. In last lecture, we have introduced the basic concepts of machine learning, which are fundamental in deriving conclusions and building theory from observational or experimental data. In this lecture, we will talk about artificial neuron. Artificial neuron is a computational unit that will help us to work with data, especially when the amount of data is large. Particularly in this lecture, we will talk about the structure of such artificial neuron and role of such artificial neuron in machine learning. Let's start with our discussion of simple linear regression. We are not talking about the general regression now. It is only simple linear regression. Simple linear regression, now we know that this is a form of supervised machine learning. Here, what we do is that we start with a training data set T, that is xi, yi, and we predict y star, which is y at x equals x star. Here, the xi is known as feature and yi we call them label. In case of simple linear regression, both xi and yi, they are real numbers. And we have n numbers of such pair that goes from I equals 1 to n, this many training data. Because the labels are known, this is known as supervised machine learning. The labels are, in a sense, supervising the learning of the computer program, which is the machine here. The computer program is the machine here. Our goal is to predict y star hat, which is y hat at x equals x star. This hat sign indicates that this is estimated value. This is not the value of y, rather this is the estimated value of y. So we build a model that gives us a relation between x and y, and from that we estimate the value of y, and that is why we are keeping this sign y hat. So y hat x star is the estimated value of y at x equals x star. Of course, to get this value of y at x equals x star, first we have to build a model that how this x and y are related. And in simple linear regression, we fit a linear model like this, that is y hat is equal to w naught plus w1x. Here the w naught and w1 are unknown and they are constants. And we try to find w naught and w1 using the training data. So this is our model. In this model, we feed the training data and it gives us the value of w naught and w1, which are our unknown. Once we get the w naught and w1, we can use this model. This model, I plug in x equals x star, and it will give me the value of y star as w naught plus w1x. This is the entire working principle of simple linear regression. We have discussed this before and we have solved problems using simple linear regression. Now let us see that if we try to represent simple linear regression geometrically, how we can do so. So here is a geometric representation. We have two nodes here. One is this blue node, one is green node. Blue node has an input of 1 and green node has an input of x. Once this 1 and x enter into this node, they are multiplied by w naught and w1 respectively. After the multiplication, both node gives their output and it comes to another node where we see that there is a summation sign. So what it will do, it will sum the inputs and give an output of z here. After the summation, it will go through a final node which will give us the output, and this final node is known as the activation node. So we have input in left side, and from left side it is going in one direction all the way up to the output. Here we call W0 as bias. W0 is something that is being multiplied with a constant input, that is 1, that is called bias. And the other part, that is W1, we call that weight. This is multiplied with the variable input, that is X. So bias is what is multiplied with the constant input, and weight is what is multiplied with the variable unit input. Then, because I am summing it up here, so my Z will be W0 plus W1X. After I get this Z, I put it in the activation function. This is my activation node. And the activation function, that is phi Z, it could be anything, but in case of linear regression, it doesn't do anything. This activation function has no role here. It's simply whatever it comes. If Z is the input, it will give us the same output. So the question is that why we are using it here? We are using it here to generalize it, and later on we will see that this activation function can do things. Many different changes it can bring in Z, but here it is not bringing any change. Whatever it is coming here, it is just passing it through. Now this structure here, what we see, that there is input, then inputs are multiplied with some scalars, then we add them up, then we pass it through the activation, and we get the output. This entire structure is something that we call artificial neuron. Why we call it artificial neuron? Because this resembles a biological neuron. So biological neuron is an unit cell in our nervous system. So these are nerve cells, biological neuron. And all these unit cells, when they come together, they make the complex neural network through which we sense different stimuli. Here also, one single biological neuron can do very simple tasks, but the entire network can perform absolutely complex signal processing. So in case of artificial neurons as well, you see that this is a single neuron and its task is very simple. But then when we combine many such artificial neuron, and when we properly select an activation function, we create something we call artificial neural network. And such artificial neural networks can perform very complex machine learning tasks, even though an individual neuron perform only very simple tasks like what we have seen here. Now this simple structure of neuron can be very different depending upon the task in hand, but there are certain similarities in all structures of neuron, and that is something we are going to discuss in this lecture. So let us expand, let us go from simple linear regression to multiple linear regression. So what was it? We now know that multiple linear regression is also a form of supervised machine learning. Here, what we do, we use a training data set which consists of xi, yi, and xi, you can see that this is bold, so xi is a vector here. Xi is our feature and yi is our label, but xi is an m-dimensional vector and yi is still a scalar, and both of them are real numbers. We use this training data set and we try to predict y star, which is the estimated value of y at x equals x star, where this both x and x star, they are obviously vectors. Now, to predict this value of y star, which is the y at x equals x star, we now try to fit a linear model. That would be y hat is w0 plus w1 x1 plus w2 x2, etc., all the way up to wm xm, because all these x are now m-dimensional. So in this model, if we give the input of this training data, we'll get the values of W0, W1, W2, etc. up to Wm. These are all unknown scalars. Once we know all the unknown scalars, what we can do is that we can give this input x equals x star in this model, and we get the output y star hat is y hat as x equals x star. That means that would be W0 plus W1 x star 1, W2 x star 2, etc. up to Wm x star m. Here x star is a vector that has the components x star 1, x star 2, etc. So now let us think about that how we can represent this operation, this entire operation of multiple linear regression in the form of an artificial neuron. So here our input has a long list. In contrast to the previous structure, now I see that my input consists of 1, x1, x2, etc. up to xm. This is simply another structure, slightly complex structure of artificial neuron, complex as compared to simple linear regression. Here also we have inputs on this side and we have output as y hat. We have W0 as bias and W1, W2 up to Wm as weights. Now we have this summation here, and summation is giving us W0 plus W1 x1, W2 x2 all the way up to Wm xm. After summation goes through the activation function, and activation function is also doing the same thing. Whatever it is taking as input, it is giving the same output. So essentially activation function is doing basically nothing here. So structurally we can see that multiple linear regression is similar to simple linear regression. The only difference is that my input is now a long list. So it gives us an impression that depending upon the problem we want to solve, we can construct many different types of artificial neurons. We can vary the activation function as well depending upon what we need. In this lecture, we are trying to find out the general structure of all such constructions possible. So let us now go toward a classification problem. We have not discussed classification problems yet, but classification problems is a form of supervised machine learning. Supervised machine learning has two parts. One is regression and the second one is classification. In the classification problem, we, just like regression, use a training data set T, that is xi, yi, n number of training data. Xi is a vector. The difference with regression here, xi is still a vector and xi is real, but y is not real. This is integer. So the label y here are categorical. They are not numerical. Categorical in the sense as opposed to numerical. What do we mean by categorical? Categorical means that this is like good, bad, pass, fail, or let us say black, red, white, green, similar type of classes. They are categorized in different kind of classes. So what we are trying to do here, we are trying to categorize this input data xi in different classes. So when I represent something in different classes, let us think about we are representing two classes. I take this data xy and I put them label they are good or bad. Some data will be good and some data will be bad. So I can write that as good, bad, but mathematically it is easier to write that in terms of integers, such as they are 0 or 1, or they are minus or 1, or they are 1 and 2, etc. So it's much easier to write in terms of integer as opposed to real numbers. And that is what we do in classification. In every other respect, it is like regression, but here our output or this label here, yi, these labels are in integer. Classification then categorizes data in different classes. And these classes are like 0, 1, minus 1, 1, etc. If the number of classes are only 2, like this 0, 1, like this good, bad, pass, fail, then we call it binary classification. Otherwise, if we have large number of classes, more than 2 number of classes, we call that multi-class classification. Now let us take a case of binary classification. How the artificial neuron in this case will look like. We will have input in left side, output in right side. We still have a bias of W0, and W1 to Wm will be our weights. Then we multiply the input with W0, W1, W2, etc. up to Wm. After the multiplication, I sum them up here in summation. So my Z here is W0 plus W1 x1 plus W2 x2 all the way up to Wm xm. And then I pass it through the activation function. Because we have a classification problem here, I have to define an appropriate activation function. One form of activation function is like this, that as soon as this Z that is incoming to my activation function that is greater than or equal to 0, will set the output as 1 and otherwise will set the output as 0. This kind of activation function is completely arbitrary. We can say that we'll set it to 1 if Z is greater than 1, or otherwise it will be 0. That way it also we can set it. And the way we'll set the activation function, that way will deduce the value of W0, W1, etc., etc. And I'll explain this with an example in subsequent lectures. But now you can see that we can have a different activation function because we want an output of 0 and 1. Therefore, this regression and classification, they lead to similar artificial neurons, but the activation functions are actually different. Otherwise, you see that this neuron is very similar to the multiple linear regression. The only difference is in activation function. In multiple linear regression, this phi z will be equal to z, but now it is giving 0 and 1. So depending upon the problem at hand, variety of artificial neurons as well as variety of activation functions we can use. Let us come to the general structure of an artificial neuron. So here you see an artificial neuron that we have used for multiple linear regression as well as for classification, and this is indeed the general structure of a neuron. So we have seen 3 cases: simple linear regression, multiple linear regression, and binary classification. So what are common to them that will lead us to the general structure of artificial neuron? So let us see the commonality. First is that they can take a vector input. In case of simple linear regression, of course, you say that this is not a vector, this is a scalar, but you can also think of that is a vector of 1 and x. So that way, that in the limiting sense, that is also a vector. So in general, it can take a vector input that goes from x0 to x1, x2 up to xm. So here, this is the input and the right hand side is the output. So this is the vector, and then it multiplies with a vector of bias and weight which goes from W0, W1, W2, etc. up to Wm. After this vector input and weight and bias are given there, all artificial neuron will first take an inner product of this x and w. So this will be this wtx, which we know this is equal to w0 x0 plus w1 x1, etc. Once this inner product is taken, we'll apply an activation. We'll activate it using some activation function var phi, and what it will do, we don't know. We have to define it depending upon the problem at hand. But at the end of the activation, we get the output. So this is indeed the general structure of an artificial neuron. The structure, you can see, that can be explained in this 4 step. This structure is very simple, but yet this artificial neuron is very useful in machine learning. And this is where I'm not talking about the network of artificial neuron. An individual neuron is also very important in machine learning. And in subsequent lectures, we'll see the importance of individual neuron. Many such neurons, of course, they work together to make artificial neural network, and they can perform amazingly complex tasks in machine learning. So now let us summarize this lecture. We have discussed the basic structure of artificial neurons. Many such neurons, they come together to create artificial neural network. Artificial neurons, they mimic in some sense biological neuron. Similarly, the artificial neural network, they mimic our nervous system or nervous system of any animal. Computationally speaking, these artificial neurons are unit cells for data processing in a computer. This is how we'll process our data in a computer. Just so, the biological neurons are unit cells for processing signals that are coming to our nervous system. So when we experience heat or cold, we touch something, that signals are being processed by a complex array of biological neurons. For your exercise, you define an engineering problem that may be formulated as a classification problem. That's all for this lecture. Thank you, and I'll see you in next class.